we are going to talk about dissociation equations and K expressions, specifically how they apply to acids and bases. First, we need to do a little bit of review. So let's revisit what it means for an acid or a base to be strong versus being weak. Strong means that acid or base is going to fully dissociate into its ions 100%. When something like HCl is put into water, it will 100% break apart to H plus and Cl minus. There will be no HCl left. All we have floating around in that beaker is H plus and Cl minus. Same thing with barium hydroxide. This will 100% break into Ba2 plus and hydroxide ions. So the way you identify whether something is strong versus being weak is you have to memorize those strong and weak acids. And we'll review that in a second, and I'll give you a memory tool if you haven't already come up with one. And the way you represent strong versus weak acids, if it's strong, we use a one-directional arrow. So when you write these dissociation equations, you use a one-way arrow because that tells me that there is no more of this reactant left. It is only ions. Compare that to something that's weak. That means it only partially dissociates into its ions. So something like H3PO4 is a weak acid. It will only partially give us H pluses and PO4 3 minus ions. And so the way we show that is with a two-directional arrow. So what that tells me is that we do get some of these ions. This produces some of these ions, but these ions can stick back together in solution to give me some of this reactant back. And it's kind of a back and forth process, and it just kind of keeps going in that cycle. We call that an equilibrium. So that's what this arrow represents. We use a two-directional arrow to show that something is weak or that it only partially dissociates into its ions. So a reminder of your strong acids and bases. There are 7 strong acids. There they are. And there are 8 strong bases. And one of the things that you should notice that the acids have in common is that they all contain an H at the beginning. So that hydrogen at the beginning is a really good indication that you're working with an acid. And then on the bases, you notice that they all have an OH or a hydroxide at the end. So that's a good clue that you're working with a base. So a memory tool, and this one's kind of silly. This is something one of my AP students came up with a couple years ago, but for some reason it's just stuck with me. So she said, hi bro, Clyde, Chloe, Chloe, so no. And that helped her remember that those were our 7 strong acids. So hi is HI, bro is HBr, Clyde is HClO4, and the Y here is kind of like a 4 if you write your 4s that look sort of like a Y. Chloe is HClO3, and 3 rhymes with E, and then Chloe is just the HCl. So H2SO4 and no HNO3, nitric acid. So that was how she remembered her 7 strong acids. There are all kinds of memory tools. You're welcome to come up with your own, or you can search the internet for some of the ones that other people have used. For our strong bases, it's a little easier because there's 8 of those. We know that they all have a hydroxide. And if you kind of look at your periodic table, they all come from group 1 and 2. So they're all here in group 1 and 2, and then we slap a hydroxide on the end. The ones that have this 2 subscript, those are the ones that come from group 2. So if you kind of draw out what looks like the letter B, those are your 7 or your 8 strong bases with the hydroxide smacked on the end, and then a subscript 2 for calcium, strontium, and barium because they're in group 2 with a 2 plus charge. So that would be a way for you to remember your strong acids and bases. And in terms of identifying whether or not something's weak, if it's not strong, then it's weak. So if you ask yourself, how do I know if this is a weak or a strong acid or base? Well, if it's not strong, then it must be weak. That's why we memorize the strong ones. So a dissociation equation. A dissociation equation is almost exactly like what we were doing when we went through the net ionic equations. We just take the substance and we write it as its ions. We balance it and we make sure we use the correct type of arrow. If it's strong, we use a one-way arrow. If it's weak, we use a two-directional arrow. So let's do a couple of those. So the first thing we have to do is identify, is it an acid, is it a base, and is it a strong acid or is it a strong base? So for HClO4, I know that that is a strong acid. And I know that it's a strong acid because I've memorized that it is a strong acid. Then we look at BeOH2. I should classify that as a weak base. And the way I know that that is a weak base is because it is not a strong base. The next one, that's acetic acid. If you recognize the C2H3O2, that's acetate ion. That was one of the ones on the list that you were asked to memorize. So acetic acid is a weak acid, and I know it's a weak acid because it's not strong. And then that last one, rubidium hydroxide, is a strong base, and I've memorized my strong base. So now I can write my dissociation equation. I'm going to split apart my HClO4 into its ions. Now remember, H is one of the ions, and then ClO4 minus is a polyatomic ion, so I don't need to split it into Cl and O independently. The ClO4 stays together. And because it's strong, I use that one directional arrow. In HClO4, that's a 1-to-1 ratio. So to balance with the coefficients, it's just ones. But if we look at BeOH2, there is 1 atom of beryllium for every 2 ions of hydroxide, and that's because we use that swap and drop to balance these charges. So when we write this, we're going to use a 2-directional arrow because it's weak, and then we have to put a 2 coefficient here to show that this dissociates into 2 hydroxide ions. Then we take a look at acetic acid, which is a weak acid, so we're going to have to use a 2-directional arrow. And again, H plus is one of the ions, but the acetate ion stays stuck together. And since both of those ions have a +1 and a -1 charge respectively, then there's no coefficients required. And then the last one, rubidium hydroxide, is strong. So we use a 1-directional arrow, and it is a 1-to-1 ratio for rubidium to hydroxide. So the coefficients are both 1. So that is how you write dissociation equations. It's very repetitive, and really the only trick is making sure that you balance the equation correctly based on the subscripts and the charges. So now let's talk about something new called a K expression, also known as equilibrium expressions. So what a K expression does is it allows us to show a mathematical relationship between reactants and products. And we can calculate a bunch of different stuff from a K, but in general, the relationship is if K is a number that's larger than 1, that means that reaction is product favored. If K is a number that is less than 1, that means that reaction is reactant favored. So in general, if we have this equation, and this is just a generic equation using alphabet letters instead of actual elements, where the capital A, B, C, D represents the element symbol, and the lowercase a, b, c, d represents the coefficient that corresponds to that. So this would be like coefficient, element A, coefficient, element B is in equilibrium, meaning it goes back and forth with coefficient element C plus coefficient element D. So these are the products, these are the reactants. So if I write a K expression, the rule of thumb is that you always do products over reactants. And so this is what that looks like. So I say K, and then this little EQ is kind of an identifier because K can be used for all different kinds of chemical situations. So this EQ just tells me that this is a generic equilibrium problem. We are going to use A and B for acids and bases in the examples that I show you here in a moment. So we just write K and then an identifier to tell us what type of equilibrium we got going on, equals, and then we do products over reactants raised to their respective coefficients. So the products here were C, and if you remember, the bracket means concentration. So I put C, concentration for the concentration, or bracket for the concentration is C, raised to its coefficient. And then I multiply it, be careful that you don't try and add these things, by D raised to its coefficients power. And then I take all of that and put it over the reactants. So element A, concentration of that raised to its coefficient. Element B, concentration raised to its coefficient. So that is the general rule of thumb. So every single equation that we have this equilibrium arrow, this two-directional arrow, is going to do products over reactants. That would be how we treat this all the time. So what does that look like if we're talking about acids and bases? Well, first thing, really important, you only need to write a K expression for a weak acid or base, because remember, we're only doing this for something that goes in both directions or has a two-directional arrow. If an acid or a base is strong, it has a one-directional arrow. That means there's no reactants left, so we don't need to write a K expression for that. When you write a K expression, you must always also write the balanced dissociation equations. Those two things go together. You can't do one without the other. And what is this all good for? Like, what do we use it for? We're going to get to a point where we can use these K expressions to calculate pH or pOH, as long as we know the concentration of the acid or base. That's how we make a calculation. So an example specific to an acid, here we have H3PO4, which again is weak. We've used the two-directional arrow to show that it breaks apart into 3 H pluses and the PO4 3 minus ion. So when we write the K expression, we say Ka, that's the identifier to let me know that this is an acid, equals products over reactants. Always products over reactants. So the products here are H plus, concentration of, so I use the bracket, raised to the third power because of this coefficient, and then times PO4 3 minus, that's the ion, raised to its coefficient's power, which is just a 1, all over the reactants, which was just H3PO4, and put that in a bracket because we're talking about the concentration of that, the molarity. That's what these brackets mean, molarity. So let's say I want us to write the dissociation equation and the K expression for HF. First thing you got to do is make sure that this is indeed something that is weak. And the way you know that it is weak, if it is not strong and you've memorized your strong acids and bases. So this is in fact a weak acid. I know this is an acid because it starts with an H. So I use a two-directional arrow to show that it is weak. And when this splits apart into its ions, the ions that make up HF are both H plus and F minus. This is in a 1-to-1 ratio because for every molecule of HF, there's only one H and one F. So this is balanced with coefficients of 1. Then to write my K expression, I write K equals, and I'm going to indicate that this is an acid by putting a little A here. So K equals, and then it's always products over reactants. So the products here are H plus and F minus. Be very careful that you remember that this is a plus in this equation, but when we put it over into K, it's not addition, it's multiplication. We use the brackets to show concentration. So the products are H plus and F minus, the concentration of those two things. And we multiply those together, and then we put it over the reactants, which was just HF. And if there were coefficients other than 1, we would raise each of these things to their respective powers. But since everything here is a 1, then we're finished. So this is a dissociation equation. This is a K expression. Let's try this one. So here we have magnesium hydroxide. Again, the first step is to identify, is it weak? And of course this is weak, and the way you know it's weak is because it's not strong. And then also you want to kind of make a mental note as to whether you're working with an acid or a base. We know this is a base because we see that hydroxide. So since it's weak, we use our two-directional arrow, and then we break it into its ions. So the ions here are magnesium and hydroxide. Now remember the charge of magnesium you can look at two ways. Magnesium's in group 2, so I know it must be a 2 plus, but also there's this little 2 here that gives me a clue about that. So this is a 2 plus. And hydroxide is one of those polyatomic ions that you were asked to memorize. So that is OH minus 1. But because of this 2 subscript, that tells me that for every one of these molecules, there are 2 hydroxides. So I have to put a 2 here to balance that. So now I'm going to write my K expression. So I say K, and since this is a base, I'm going to use my little identifier to say KB. Let me know it's a base. And then it's still the same. We just do products over reactants raised to their coefficients powers, if there is one. So the product is Mg2+, and that 2+ goes inside the bracket because that's just identifying the charge of this magnesium. And then OH-, but that 2 coefficient goes on the outside as a power, as a exponent. So be careful about that. This 2 stays with the magnesium because it's part of its charge. This 2 goes on the outside because it's a coefficient. And then we put it over the reactants, which was just MgOH2. And we're done. Let's do one more. Let's say we have H2S. Again, we check to see is it an acid or a base. If it starts with a hydrogen, that's a good clue that it's an acid. Then we check to see is it weak or strong. This is weak, and we know it's weak because it's not strong, and we've memorized our strongs. So 2-headed arrow, break it into its ions. Make sure we're balanced because sulfur is a 2- charge. That means it takes 2 hydrogens to balance this molecule. And so we put a 2 coefficient here. So when this dissociates to its ions, it's going to split into 2 hydrogens and 1 sulfur. And then we write our K. This is a Ka expression because this is an acid, equals products. So H+ raised to the 2nd power because it has a coefficient, times S2- raised to the 1st power because it does not have a coefficient, or the coefficient is 1, over concentration of H2S. And that's it. That's how you write a dissociation equation and a K expression for either acid or base.